Hello and welcome to week 6 of the massive open online course for the University of Nicosia's master's degree in digital currencies. I'm your teacher, Andreas Antonopouloss, and I'll be answering your questions that you posed on the forums throughout the week. Some good questions, some great conversation on the forums, and of course I'll also be dipping into the chat to see if you have any follow-up questions that might be relevant, although the questions from the past week take priority because you've had more chance to prepare on those. So welcome all, and let's get started. Elena asks, could you please comment on why Bitcoin has such a strong community compared to other open, public, and permissionless blockchains like Litecoin, Monero, etc.? What are its strengths and maybe their vulnerabilities? Elena, it's really difficult to pick what specific principles or reasons there are behind a very strong community. I think we can look at it from two different perspectives. The first one, of course, is that Bitcoin started it all. And so it's had 10 years to build both recognition of its name and a very big community. Pretty much every other community in the open blockchain space starts with people who first encountered Bitcoin. So that's a huge advantage. That's the first mover advantage, as is known in technology circles. But I don't think that's the only reason. I think another very important reason is that Bitcoin has a set of very, very clear principles and very, very clear reasons for why it exists, why it matters, and what it can be used for. And it's very difficult for many of the other open public blockchains that come later to express such a clear sense of purpose. If they express principles and reasons that are very, very close to Bitcoin, then they don't differentiate enough. So if you say, well, this is kind of like Bitcoin, only a bit better in this one area, that's not different enough. And most people will stick with what they know. They'll stick with what is more recognizable and the first thing that express these principles more clearly. So it's very difficult to compete without differentiating enough. And yet, if something differentiates enough or a lot, then it's not competing directly against Bitcoin, and therefore it may not be as easily recognizable as belonging to the same general category of things. So that's one of the big reasons I think Bitcoin has such a strong community. A clarity of purpose, clearly defined principles that started this entire space, a set of design decisions that clearly resonated and made Bitcoin successful over the first 10 years, and it's very difficult to compete against that. The next question is about stages of development of the Ethereum blockchain, and there's one question and a follow-up from the forums. Milton asks, what stage out of the 4 is Ethereum now in? Serenity? What is the significance of reaching the 4th stage? So Milton, the 4 stages of Ethereum's development roadmap were defined right at the beginning, and that development really got derailed. And it got derailed for a number of reasons, including scalability issues, as well as some difficulty in implementing proof of stake. So Ethereum originally was intended to transition to proof of stake as early as possible, and that transition was encouraged by a mechanism called the difficulty bomb. Now, that difficulty bomb made the difficulty of mining Ethereum escalate, thereby slowing down Ethereum and requiring successive hard fork changes in order to diffuse the difficulty bomb, as it's known. This was a mechanism to ensure that Ethereum's development didn't stagnate or that proof of stake wasn't forever postponed. So this mechanism is essentially to keep the miners in check and not give them power to veto proof of stake. However, as this was happening, the development of proof of stake became coincident with the development of scaling solutions, meaning that the Ethereum developers decided that the best way to implement scaling solutions was at the same time as implementing proof of stake, and that the two worked hand in hand. This meant also a fundamental philosophy change in how proof of stake was going to be implemented. So proof of stake was not going to be implemented as a retrofit to the Ethereum chain, but instead through the implementation of a rather expansive vision that included a beacon chain, as it's known, a sharding infrastructure with 64 shard chains that run in parallel to the beacon chain, and that transition is called Ethereum 2.0. So the original roadmap for Ethereum has effectively been abandoned. Ethereum will not transition to the fourth stage of Ethereum's development simply because there's a new roadmap. And that new roadmap is to build a completely clean slate implementation of Ethereum called Ethereum 2.0, and then to migrate the existing chain into Ethereum 2.0 as one of the shards. This allows Ethereum to transition both to proof of stake as well as implement a scaling solution called sharding that allows up to 64 times increase of the number of simultaneous operations. And all of this is coinciding with a bunch of other developments also. So, bottom line, the original roadmap of Ethereum does no longer apply. Now Ethereum has a new roadmap. That roadmap is Ethereum 2.0. It's involved an additional 2 years of research, and it is currently in progress. The final testnet for Ethereum 2.0 is now live. It's called Spadina, and Ethereum 2.0 will be transitioning to a live mainnet launch by the end of 2020. Jonathan then asks a follow-up question. To add to this question as it relates to the current stage, Serenity, how is it decided when things are ready for the next stage? I assume it is reviewed among the developers with active commits and voted on by validators and miners. Is there any one person steering the decision with more weight than others? For example, Vitalik Buterin. So Jonathan, this whole roadmap discussion has taken many twists and turns. And Vitalik certainly has significant influence because of the respect afforded to the initial inventor of Ethereum. But Vitalik doesn't really decide on this. The decision is made by all of the developers who participate in the core developer meetings, and also with input from the broader developer community. There are a lot of people involved in these conversations, and often ideas that were not Vitalik's, such as ideas on building proof of stake in a variety of mechanisms, are brought forward by other developers and follow their own path. A great example of this was the proof of stake mechanism proposed by Vlad Zamfir, called Casper Correct by Construction, or Casper CBC. This was an alternative to Vitalik's proposed Casper FFG, the finality-friendly gadget, and an alternative approach to proof of stake. The two research paths for the two different versions of proof of stake proceeded in parallel. And they, in fact, competed in many ways. And now Ethereum 2.0 is going to be implementing Vitalik's proof of stake first as a hybrid solution with proof of work, followed by a transition to Casper Correct by Construction that was initially created by Vlad Zamfir. So I think people who are outside of this process perhaps think that Vitalik simply says and things happen, but that's not how it actually works. Ethereum's development process is very much a technocracy. Ideas are judged on their merits. Vitalik often makes proposals that are not followed by anybody else, and in fact are vigorously debated, and Vitalik's opinion is treated the same as anybody else's opinion. Obviously, he's given the respect that is due for someone who has had so many great ideas, but his ideas don't automatically win, and they don't get more respect just because he's Vitalik. So in fact, it's a fairly open, meritocratic, technocratic-based process. And if you want to, you can participate in these things. So you can participate in the meetings of the Ethereum core developers and basically see how debate is handled, how proposals are brought up, how things are debated both in those meetings and in the pull requests that are happening on GitHub, how various issues are hashed out, and how different developers get to express their opinions. There's a follow-up question on the chat I'm seeing from Elena about Ethereum having some problems with 51% attacks. Actually, the 51% attacks have been on Ethereum Classic, not Ethereum. So Ethereum Classic is a fork that happened after the DAO, and Ethereum Classic is on much less hash power for its proof of work, and as a result has been subject to 3 51% attacks so far that have set back that chain and damaged it quite a bit. But this is different from Ethereum, or Ethereum 1 if you want to call it that, which has not been 51% attacked. All right, the next question is about Ethereum's total supply. Daniel asks, there has been some discussion about the real total circulating supply of Ether. Some argue that the real supply is way more than the official account. Is that so? And if it is, are there any implications for the future of the project? Is Ether money? Daniel, this debate raged a couple of months ago called the ETH Supply-Gate debate. And it was honestly mostly a debate started by Bitcoin adherents who wanted to make a point. I don't think they actually achieved that point or made that point very well. And I did say so publicly at the time, but it's a very controversial topic with a lot of very, very acrimonious debate. The bottom line is that Ethereum's supply is a bit more tricky to calculate, and there isn't, at the time, a straightforward API call that you can ask one of the Ethereum clients, what is the total circulating supply? There are a number of reasons why it's a bit more tricky to calculate, including the differences between the UTXO model and the account model that Ethereum uses, as well as the mining algorithm that has not only the winning block, but also additional blocks called uncles or omers. And those come in sometimes a bit later than the winning block and have to be counted and also have some of the reward given to them, which changes the final supply. So you can calculate the Ethereum total supply. You have to set a specific point in time, and because Ethereum blocks happen on average every 15 seconds, you may get a different answer if you refresh a page earlier than somebody else. If you're looking at this, for example, on a website, and a lot of the websites were calculating it incorrectly. The bottom line is that it is possible to calculate the real supply. It is possible to calculate the real supply with absolute accuracy, just like in Bitcoin. You have to decide which block you're calculating it for, and you can run a simple script that adds it all up. And there's a couple of different ways to do that. You have to decide if you're going to take into account Ether that is burned for example, or not, the same kind of decision you'd have to make for Bitcoin. It's a bit more difficult to calculate it by adding up all of the account balances than it is in Bitcoin to add up all of the UTXO, but it's still possible. And it's also possible to calculate it by adding up how much was issued up to a certain block height, just like you can in Bitcoin. So if anybody argues that the real supply is more than the official supply, that's not actually the case. So anybody who was arguing that was not arguing in good faith. In fact, you can calculate the supply of Ether. Now, the interesting question is Ether money? And in my opinion, the answer is yes, Ether is money, but it's not primarily money in that, in the same way that Bitcoin is primarily money. Ether is a metering and accounting mechanism for gas, primarily, and secondarily money because its utility gives it value and it is used to collateralize various DeFi contracts. So it has the function of money, or it has some functions of money. It is used as a medium of exchange. It is also used as a store of value for the collateralization of DeFi things like stablecoins, decentralized stablecoins on the Ether platform. It's just that it's not primarily money. Its primary function is for metering the computation of smart contracts and essentially for gas. So Ether is money, but not primarily money. Let's see if there are any additional questions in the chat while I have a quick sip of coffee. Chuch asks, when mastering Ethereum 2.0? There won't be a mastering Ethereum 2.0, but there will be, I hope, a second edition of mastering Ethereum at some point over the next year and a half that will add information about Ethereum 2.0 in the book. So mastering Ethereum as a book really is not about the consensus algorithm or how Ethereum is mined or any of that. It's mostly about the smart contracts environment and how that operates and how to use it. And so there's a small part of the book that's about the consensus algorithm, but it's pretty small. And that part of the book will be essentially upgraded with more information about how Ethereum 2 works, the transition roadmap, and all of that. But I haven't started work on that. I'm currently working on another book. So thank you for asking. We are going to work on that soon. CX asks, what time is it, Andreas? It's Bitcoin time. This is a running joke for the MOOC and some of my other videos. All right, let's see. Rahul asks, how are Ethereum blocks added that much faster than Bitcoin blocks? Rahul, that's because the consensus algorithm that Ethereum uses for mining, the proof of work algorithm, is completely different. The design decisions made in Ethereum are very different from the design decisions made in Bitcoin. So Ethereum uses a different algorithm. This algorithm is a proof of work algorithm, but it does not use SHA-256. It uses SHA-3. And it's purposely designed so that it's not that easy to make ASICs. And there have been a number of attempts to undermine the development of ASICs. So Ethereum is mined on GPU. Furthermore, the block issuance schedule is completely different, blocks every 15 seconds. And as a result, there are a number of other parameters that are tweaked in order to make sure that this doesn't cause continuous consensus forks because of the rapid issuance of blocks. But in general, completely different design decisions from Bitcoin. Artem asks about the limitations of smart contracts. What are the limitations of smart contracts? Can they be integrated into almost every sphere of society? I feel like there is a lot of hype in the space, and most of it seems to be far from reality. For example, some envision autonomous corporations or DAOs replacing existing corporate structures and contributing to economic value creation. Is that possible? What is the best case scenario for smart contract integration into the real economy? Artem, I'll agree with you that there's a lot of hype in the space because people have a very expansive vision, and very often they won't say exactly when they expect these things to happen, just a kind of long-term view of how this type of technology might change society. I think probably the idea of autonomous corporations, or not completely autonomous, but decentralized corporations or new corporate structures that are built on smart contracts isn't in fact that far-fetched. I think that is probably one of the strongest arguments you can make for smart contracts. We already have decentralized autonomous organizations that offer governance models for a variety of financial instruments. For example, for decentralized stablecoins, for decentralized exchanges, for various prediction markets and things like that, for crowdfunding solutions, etc., etc. All of these are, to some degree, decentralized organizations, although they're not autonomous. There have been some attempts at autonomous organizations, but the technology hasn't matured enough, and there are some significant risks. However, that doesn't mean that this isn't already happening. There are somewhat autonomous, somewhat decentralized organizations running on smart contracts that replace some of the structures of traditional governance you see in corporations and are generating economic value today. And so that is happening. Whether it will happen to an extent where all corporate structures are replaced, I don't think so, but it is very likely that significant economic activity can occur on more decentralized organizations and more autonomous organizations using smart contracts than we have today, and that will change the way corporate governance works. So I don't think that's too much hype. Some of the hype has to do with smart contracts replacing all kinds of governance models and social cooperation models in the world. And of course, I think that is probably far-fetched, certainly in the short term. But that doesn't mean that these things can't have a very significant impact in some spheres of corporate governance, or that they can't have significant impact on the development of financial models, financial instruments, and things like that are much more decentralized than what we have today. Some of the interesting problems that come up with this have to do with oracles. For example, how do you take information that is outside of the smart contract, such as real-world conditions, information from other things like feeds about the exchange rate of Ethereum to the US dollar, which is used in stablecoins, for example, in a way that's decentralized. These are difficult problems to solve, but that doesn't mean they're not solvable. So when we talk about smart contracts and what they can do in the future, the oracle problem, as it's known, is one of the areas where there's a lot of research and a lot of interesting things happening. Another area is how to balance the amount of governance that is done by humans versus the amount of governance that is baked into the smart contract. If you create a completely autonomous smart contract, like the original DAO, or almost completely autonomous smart contract, the risk is that if there is a vulnerability or loophole, that can be exploited, and there's no way to fix that. And we saw that with the original DAO. Since then, various DAOs that have been built have some degree of governance built in that allows people to override in the case of a vulnerability, of course. That leads to the opposite problem, which is, what if the governance mechanism can be hijacked? Or what if the governance mechanism, leads to a single point of risk where those who have control of the governance can basically steal from the smart contract or hijack it for their own goals. We've seen both of those. We've seen exit scams through the governance mechanism, and we've also seen bugs in the governance mechanism leading to problems. So this is still an area where there's a lot of development. Finally, the third area where you need more development to overcome the limitations of smart contracts is scaling. And of course, that's what the Ethereum 2.0 roadmap is about. If every time a smart contract becomes popular, whether that's CryptoKitties in 2017 or some form of DeFi today, if every time something becomes popular, the gas fees skyrocket, the capacity of the chain becomes limited, and that scalability has an impact on the execution of smart contracts, as we saw with problems in the MakerDAO system during the price meltdown and gas price increase in March. Those will have secondary effects. So these are still weaknesses of a smart contract system. So scaling is the next area. As these problems get solved, the domain of what can be done with a smart contract expands. So you can do this much today, and then if you solve some of the problems, you can do more, and then more, and then more. So it's not a question of whether smart contracts have succeeded or not. It's more about a degree. So have they succeeded in doing this much so far? Arguably, yes. Can they succeed to do this much? That depends on whether many of these engineering challenges, governance challenges, etc., vulnerabilities, and the maturity of the technology will allow us to reach that scale, and when. So I think that's something we can't really predict. Gregory has some follow-up questions about smart contracts and mining. Gregory says, I understand a block in Bitcoin, but with Ethereum, it boggles the mind. A transaction can send data to a contract. The contract can result in multiple outcomes. So does every node miner execute all transactions if sufficient gas? But what needs validating? Who wins the block? Gregory, this is a great question, and it's something that isn't immediately obvious when you start studying Ethereum. So to answer your question, yes, every node and every miner executes every transaction against the current state in the Ethereum virtual machine, running through all of the execution, calling contracts, passing data to these contracts, allowing them to execute and call other contracts, etc., until either the execution ends successfully or the transaction runs out of available gas, in which case it gets an insufficient gas error. This is required to validate a transaction. So a transaction in Ethereum is valid not only if the data inside it is valid, as in Bitcoin, but also if the execution of the entire smart contract chain is valid and reaches a conclusion. So similarly in Bitcoin, you can imagine that in order to validate a transaction, every node and every miner has to execute the Bitcoin script to see if the signatures or whatever other script execution requirements are met. Well, in Ethereum, every miner and every node has to execute the script and run it through the Ethereum virtual machine and see if it arrives at a valid conclusion. This is why gas exists. It's to ensure that nodes and miners do not end up using too much time trying to compute a transaction that causes too much execution. So it constrains the maximum amount of time that nodes and miners will take validating these transactions. Assuming that the transaction finishes successfully, that is then a valid transaction, which means it can be included in a block and it can move forward the state of the Ethereum system. Miners include all of these transactions in a block, and then they do similar job to how you would mine a Bitcoin block. They try to find a nonce for the block that allows the block to have a proof of work hash for the block header that is below a specific difficulty target. So all of that is pretty much the same. The miner who finds a block first broadcasts that block to everybody. Everybody validates all of the transactions in that block and then incorporates it into their local copy of the blockchain. And that changes the state of all of the accounts and smart contracts that were affected by all of the transactions in that block. And so the blockchain state moves forward one step. And this continues. So it's very similar. The only difference is that when validating a transaction, everybody runs all of the smart contracts that are executed by that transaction. Georgios asks, are smart contracts something like derivatives? No, George, the term smart contracts is very confusing, so I would like to replace it with the term dumb programs. Smart contracts are not smart, and they're also not contracts. They are dumb programs. They're software programs written in a bytecode language for the Ethereum virtual machine, but effectively often written in a higher level language called Solidity. And you can read that. It kind of looks a bit like JavaScript. It will seem familiar syntactically. If you can read that program, they're not that difficult to read. You can understand what the transaction would do when executing a specific smart contract with specific data. So a smart contract is a program. It's called by a transaction that executes it with various parameters, and then it produces a result. That result may also change some variables. It may store some data. It may retrieve some data. And ultimately it will return some kind of result. So it's a program. Alexander asks, can smart contracts work with bonds? There is an example in our reading material of bonds, which are smart contracts to automatically pay interest payments and principal upon maturity. This does not seem to make real-world economic sense. Ordinarily, an issuer borrows funds from the investors via issuing a bond to fund a productive but somewhat risky enterprise. But the proceeds of the bonds are being invested, which are expected but not guaranteed investment returns, etc., etc. If a smart contract is used as described in the example, in order for it to work, all funds that are raised as a bond principal will have to be reserved on the blockchain, where the smart contract can automatically guarantee repayments. Yes, that's correct, Alexander. That use case example really refers to more of an insurance bond rather than a traditional financing or borrowing bond. However, as you will find, there are a number of decentralized finance instruments that operate as a lending facility, and this lending facility depends on collateralized loans. That's where people deposit a certain amount of Ether, and then that can generate interest by lending to others. In order to do that, you have to have an over-collateralization, meaning that there is more collateral in the lending facility than the amount that you withdraw. And there are some risks. The default risks there also relate to the price of the underlying asset. So if Ether's price drops in the market, then your loan can become under-collateralized, in which case it gets liquidated on a secondary market. This, in fact, happened in March when there was a sudden and precipitous drop of the Ether exchange rate, well, pretty much all cryptocurrencies, and at the same time, gas prices went through the roof. So that system has some internal risks, but also some external risks. But there are lending and borrowing facilities using collateralized loans. If you're interested in more, you can look at the DAI system, DAI from MakerDAO, and look at the DAI savings rate, which is basically a mechanism for you to deposit Ether and earn interest from it by having a small part of it being lent out to borrowers. Daniel asks about proof of stake versus decentralization. Another interesting discussion taking place about the centralization movement that the change to proof of stake may bring due to the financial power of some validators. Is that so? Could you please comment on that? Well, there are arguments that... oh, sorry about that. Let's try that one again. Car alarm went off in the background. Daniel asks, another interesting discussion taking place is about the centralization movement that the change to proof of stake may bring due to the staking and financial power of some of the validators. Is that so? Yes, so Daniel, there's an argument that proof of stake will lead to centralization due to the idea that those who have the ability to put a lot of financial stake at place will end up gaining most of the gains. So this is the idea that the rich get richer through their proximity to capital. In economics, this is known as the Cantillon effect. And it's based on an idea by an economist that those who are closest to capital get the most benefit when there is a distribution of capital. So this idea certainly has merit. A lot of people also argue that proof of work has a similar centralizing effect, which we've seen in practice in Bitcoin. And that is that in that case, the capital isn't implemented in the form of a cryptocurrency like proof of stake, but it's implemented in the form of silicon ASICs, tens of thousands of silicon ASIC machines in massive warehouses that also create economies of scale and massive advantages for those who can deploy very large amounts of capital. Now, whether that will happen in Ethereum 2 or not remains to be seen. The Ethereum 2 mechanism is a proof of stake mechanism that requires 32 Ether to become a validator, and of course, validators with bigger stake gain an economy of scale. However, keep in mind that if you stake very large amounts of Ether, that also means that you are risking very large amounts of Ether. So Ethereum is a staking system that has slashing. And slashing is where if you break the consensus rules or you go offline and inadvertently break the consensus rules by not validating when you should, the end result is that you lose some of your stake. And so therefore, if you think about it, those who risk very large amounts of capital also risk getting slashed. With much larger amounts of capital getting slashed. So it's very difficult to predict how this is going to play out. Will proof of stake have some centralizing pressure because of the Cantillon effect? Probably, yes. And I don't know if that centralizing pressure will be more or less than proof of work that centralizes control increasingly in the hands of those who have the biggest industrial infrastructure. That remains to be seen. Astrid asks about bridges between different blockchain types. It seems that developers of a particular blockchain are always keen to build to build a bridge to address scalability, tap into other dev ecosystems, etc., such as bridges between Bitcoin and Ethereum, Polkadot and Ethereum, etc., etc. How do these practically work? And how often are these used in practice? Not very often, Astrid. There are a lot of discussions about bridging various blockchains, and at the moment the mechanisms for bridging blockchains are not very sophisticated. The primary mechanism for bridging blockchains comes in the form of decentralized exchanges, and there aren't that many decentralized exchanges that bridge multiple blockchains. But the idea here is that you want to make it as easy as possible to move capital between the blockchains without a trusted third party, so without using a centralized exchange. This can be enabled through a mechanism called atomic swaps. And atomic swaps isn't a specific technology, it's more of a general concept. An atomic swap is a swap where two parties on different blockchains can deposit collateral in such a way that they can agree on a swap between one cryptocurrency and another on two different blockchains, for example, where neither party can walk away with their money without the other party also getting paid. Atomic, meaning that it is an indivisible operation. Either both parties get a refund and nothing happens, or both parties get paid and swap their cryptocurrencies, but you can't cheat. And this is a mechanism that takes advantage of some very basic cryptography in order to ensure the atomicity of the operations. Basically, spending the cryptocurrency on one blockchain automatically reveals the secret that the other party needs to spend the cryptocurrency on the other blockchain, so that no matter who goes first, the other party is guaranteed that if their money is taken, then they can also take the swapped money from the other person. To keep it relatively short, atomic swaps are the most common bridge between blockchains, but increasingly we're seeing this evolve a bit to second layer solutions that try to connect blockchains with second layer protocols. Basically, think of that as payment channels between blockchains that bridge various second layer solutions. These are still in very, very experimental stage, and we haven't really seen much use. Some of the blockchains that are being developed, you mentioned, for example, Cosmos and Polkadot, have as their primary objective bridging multiple blockchains together and kind of standardizing the mechanisms by which you can easily move capital from one to another, and potentially even in the future move state so that you can execute smart contracts in such a way that you move state across blockchains. But again, these are very, very early stage. Dimitris adds a note that both Polkadot and Cosmos are explained in the master's degree. They're not part of the MOOC, so just a brief mention here of what those are, but we won't go into any more detail. Let me check in the chat and see if everything is good. All right, and let's continue with the questions from the forums. Kima asks 3 questions about permissioned and centralized blockchains. If a blockchain becomes heavily permissioned, is that not akin to centralization? Absolutely. The ability to withdraw permission to participate is a very powerful aspect of centralization. If a central party or power has the ability to control who has access to a blockchain, that gives them enormous power to include or exclude to their own interests. And so that is very much a form of centralization. In fact, the ability to participate without having to ask for permission, without authorization or vetting, is a key principle, an underlying pillar of open public blockchains. Without that, they're not open. The second question is, would it be possible a situation where Ripple and Corda integrate to deliver a peer-to-peer solution that will dematerialize traditional banking? I don't know if it will be any of those particular solutions. I do think that traditional banking is going to head in a direction that is more decentralized, but not actually decentralized. So more decentralized than traditional finance, which is very centralized, in a more federated model and probably using something that kind of looks like a blockchain, but with a permissioned and control system that retains centralization. So these types of traditional finance systems that are based on blockchains will not be open, they won't be public, they won't be decentralized. They won't be borderless, they won't be immutable, they won't be neutral, they won't be censorship resistant. They can't be any of those things because they have to support the existing regulatory system. Which leads us to the third question. Will increasing regulation in the crypto world signal the end of this promising technology? I certainly don't think so. I think it's the opposite. I think increasing use of this promising technology may signal the end of a broken regulatory system. No amount of regulation from any local jurisdiction will change the fact that this is a global technology that can be operated from anywhere, that can pick jurisdictions that are more friendly in favor of jurisdictions that are less friendly, and that can transcend borders using communication protocols that are very, very difficult to limit or stop. So the issue is not the increase in regulation. The issue is the inability to enforce that regulation on a global basis. And there is no way to enforce a single regulation on a global basis and impose that on a communication technology that can operate over any open communication system. So increasing regulation in the crypto world will not end the promise of this technology, because the promise of this technology is that it is open and decentralized and cannot be shut down from a central authority. That is the promise. And that promise becomes more and more necessary the more there is an attempt to regulate this technology into submission. Peter asks, what is there to stop someone or some group from cloning Bitcoin, call it BTC2, start a new blockchain but mimic the operating process and protocols exactly? I realized that Bitcoin wouldn't be interchangeable and remain separate systems, but they would have the exact same characteristics. If this is correct, wouldn't it have a disinflationary effect on Bitcoin's value? Peter, not only does nothing stop people from doing this, but it has been done dozens and dozens of times. When this is done, it's called a fork. And a fork is when someone splits off from the existing Bitcoin system in order to create a parallel system that may or may not be interoperable and may retain some or all of the characteristics of Bitcoin under a new name. This has been done, I believe, more than 50 times to Bitcoin, with more than 50 Bitcoin forks, as they're known. From the first fork that happened in August 2017, called Bitcoin Cash, to subsequent forks like Bitcoin Satoshi Vision, BSV, and then dozens and dozens and dozens of other Bitcoin forks. Bitcoin Gold, Bitcoin Diamond, Bitcoin Platinum, Bitcoin this, Bitcoin that, all of which attempt to do exactly what you said. It doesn't have a disinflationary or inflationary effect on Bitcoin. In fact, it has very little effect on Bitcoin itself. What it's proven is that these other systems, just like any other form of cryptocurrency or blockchain that can be created without any barriers, do not affect what happens with Bitcoin. People can create thousands of cryptocurrencies, and that doesn't change the value of Bitcoin, and it also doesn't automatically give value to these new cryptocurrencies just because someone created them. The hardest thing now in the new monetary space of cryptocurrencies is not the creation. In the old world of monopoly currencies, where there were 194 national currencies created by governments, kings, and emperors, then the hard part was deciding to create a currency by fiat, and then you could impose a monopoly that forced everybody to use it. That getting people to use it was the easy part because it was created under monopoly conditions and with the imposition of this monopoly by fiat. With cryptocurrencies, the opposite is true, which is that anyone can create a currency, but no one will use it unless they find it useful. And so thousands and thousands of cryptocurrencies have been created Most of them are completely worthless, and they can't get anybody to use them. And that includes most, if not all, of the Bitcoin forks that have very, very little use compared to Bitcoin itself. So this is happening right now, and it reveals this fundamental truth that whereas before the difficult thing was creating and the easy thing was getting people to use it, forcing them to use it through monopoly, once that monopoly is broken, it's very easy to create, but you can't get anybody to use it unless they find it useful, and most of these things are not found useful and are therefore not used. Let's see, just going to do a quick time check. We've got 10 minutes, which is just enough time to answer Gregory's question about transaction malleability. This is from last week, I believe. And this is a topic that a lot of people find difficult to understand. It's not an easy topic. So, transaction malleability, where is the actual attack taking place? Gregory asks, I'm struggling to get my head around what causes the actual weakness due to transaction malleability. From a high-level perspective, from what I understand, this issue is caused by the fact that the signature script can't be hashed since it's required to unlock one's unspent outputs. From a high level, yes. The signature script can't be hashed and signed because that would create a circular dependency. You can't sign the signature because the signature changes the signature, which then needs to be signed by the signature that changes the signature, which then needs to be signed by the signature. You can't unravel that. The reason you can't sign the signature itself is because its value determines the signature. So you can't, in a circular dependency, make that happen. So the signature itself is not included in the thing that you sign. That means that the SIG script itself is the part that's vulnerable because it can be malleated. Yes. Gregory asked, but at what point does the vulnerability occur? Is that once the transaction is available in the mempool? Yes, exactly. Once a transaction is broadcast and is available in the mempool, a third party can malleate it by changing the contents of the SIG script and producing an alternative version of the transaction that has a different transaction ID. So more specifically to Gregory's question, can a hacker modify a transaction in the mempool? No, they can't. It's been broadcast. It exists in many mempools. There is no one mempool. Every node has its own mempool. So every node has a view of that transaction, and you can't go and modify something that's in somebody else's mempool. 4b, does the hacker create a copy of the transaction with a modified SIG script? Yes, exactly. That's what happens. So the hacker who's doing the third-party transaction malleability produces a second transaction that is identical in all ways to the original transaction. It has the same inputs, it has the same outputs, it pays the same amount to the same destination addresses, all of that. The only difference is the SIG script is slightly different in such a way as the new transaction has a different transaction ID. So Gregory concludes, in the latter case, we end up with two identical transactions but with different hashes IDs. One of the transactions won't compute for the unlocking script, I assume, meaning it won't be valid by miners. No, that's not the case. Both transactions are valid. Both transactions will compute. The changes made to the SIG script are such that they mathematically compute, but they produce a different hash. How do you do that? How do you create a SIG script that is still valid, that still computes correctly and unlocks the funds correctly, but produces a different hash? This is the interesting thing to understand with transaction malleability. So let's think about this arithmetically. Let's think about, let's say the signature itself is an arithmetic operation, and that arithmetic operation is 2 plus 3 equals 5. right? So it should be 5. The SIG script says 2 plus 3. And if you calculate 2 plus 3, you get 5. That's the correct answer. How can you change that in such a way that the equation is different, but the answer is the same? Well, you can do something called a nilpotent operation, meaning an operation that doesn't change the outcome. In arithmetic, that would be adding a 0, for example. So if we do 2 plus 3 plus 0, that's a new subscript. It's completely different. It's got a whole other number in there. It's 2 plus 3 plus 0. But the result is still 5. And if you were computing that as a subscript, and that SIG script had to be 5, the result would be accurate, and you still get 5, which means it's still a valid SIG script. It still unlocks the script pub key because it results in the correct result. But if you hash 2 plus 3 plus 0, it gives you a different hash from 2 plus 3. Obviously, there's some different data in there, which means that you manage to malleate the subscript to change the ultimate hash of the transaction without changing the effect of the SIG script, which is to produce a valid transaction. And what that means is that you have two identical transactions, both of which are valid, both of which unlock the inputs and spend them correctly, but they have two different transaction IDs. So this is where we have a problem. Now, the miners can choose one or the other, and it really depends on which one they see first. They can't choose both, because obviously you've got an attempted double spend. Both of these transactions that are identical are spending the same inputs. If one of them is valid, the other one isn't, because the inputs are already spent. But it depends on which one comes first. So miners will look at this and take the transaction they see first as the valid one, and then they will reject the second transaction as an attempted double spend. So if the malleated transaction injected by the hacker ends up getting mined, then the original transaction that you broadcast ends up getting discarded. And if you think about it, that depends on how the hacker injected into the network. Maybe they received it in their own mempool, malleated it, and then injected it directly to a miner in order to take a good chance that it's going to get there first. And so as a result, because it doesn't take the long way through the network by being broadcast from node to node, the hacker's malleated transaction will get mined first. Now, this is a probability game. A lot of the malleated transactions won't get mined first, and therefore nothing happens. But every time it happens, every time one of the malleated transactions get mined, what ends up happening is that the transaction ID that is recorded is incorrect, or at least is different from the one the original transaction had. And this can cause a number of secondary effects. Let's look at two of these effects. The first effect, which was the one that was really noticed in 2013 and is one of the contributing reasons that the original exchange, MTGOX, failed, was that if you have miscoded your Bitcoin application to assume that transaction IDs are final, and therefore look for a transaction ID to decide whether a transaction has been accepted in the mempool, or rather has been mined in the blockchain, you will not see your transaction ID even though those inputs have been spent. This was exploited by people doing multiple withdrawals. MTGOX was looking for transaction IDs, was assuming that a withdrawal was unsuccessful because they could not see the transaction ID mined in the blockchain, even though a malleated transaction had spent those inputs, and so the withdrawal had in fact happened. And they would then authorize a second withdrawal, which would allow the attacker to withdraw the money again and again and again, eventually draining the MTGOX hot wallet, which was then replenished again and again and again, eventually draining all of MTGOX. So One way that transaction malleability can be exploited is if you have a badly coded application. An application should always look at the inputs. Has the UTXO itself been spent or not? That's how you decide if spending has happened. You do not look at has the specific transaction ID been accepted, because, at least before transaction malleability was fixed, that is not a reliable mechanism. All right, so that's one. But there's a bigger and deeper problem here, and it has to do with chained transactions. Now, transactions don't always go by themselves. Sometimes they go as part of a packet. And this is where you have several transactions that depend on each other. You have a parent, followed by a child, followed by a child, followed by a child. These are transactions where you have a transaction that creates UTXO, then that UTXO is spent in a child transaction that creates new UTXO, and that transaction output is spent by another child. So you would have a parent, child, grandchild, etc., all the way down. These chains of transactions sometimes get confirmed together in a packet. And you want to be able to do that for a variety of reasons. One is for fee management, for example. This is the mechanism used in child pays for parent. But here's a very important one. If you are holding back previously signed transactions and you don't want to broadcast them until something has happened in a layer 2 protocol, then you need to ensure that the parent still exists. Let's say, for example, you have a Lightning channel. And in the Lightning channel, you have an initial funding transaction, and then you have a commitment transaction or a refund transaction that depends on that. Well, you need to be able to make sure that you can spend your refund transaction to get a refund if something goes wrong with the channel funding. The refund transaction will be spending the inputs of the original parent. How? By referring to those through its transaction ID. Now, if, on the other hand, when you try to broadcast the refund transaction, the attacker has malleated the funding transaction and changed its transaction ID, well, now the refund transaction you have is invalid. And the reason it's invalid is because it has the transaction ID of the parent that never got confirmed, because instead a malleated parent got confirmed with a different transaction ID. So you're holding a signed refund transaction that is chained as the child of a transaction that never happened because of transaction malleability. For layer 2 protocols to work, you need to have a guarantee that even if a transaction hasn't yet been confirmed, its transaction ID cannot be modified because you have children that depend on that transaction ID that are chained, that are signed by the other party in a layer 2 protocol, and that is your only guarantee of getting your money back. So if the other party can simply malleate the transaction that funded this, get it confirmed and invalidate your refund, they can cheat. Transaction malleability had to be solved for layer 2 protocols to work, because layer 2 protocols depend on strong chains of parent-child transactions that can be held back and transmitted later, but that cannot be malleated by one of the parties. Transaction malleability had to be fixed for layer 2 protocols, for pretty much any layer 2 protocol, for atomic swaps, for a variety of other protocols to be built on top. And segregated witness fixed transaction malleability so that now you can be assured that if you have a refund child transaction, the parent will get confirmed with that transaction ID and cannot be double spent with a different transaction ID. All right, hope you enjoyed that little segue into transaction malleability, a difficult topic. Gregory, thank you for that question. That was a lot of fun to answer, and I hope it clarified the topic. You seem to have gotten new clarity. And with that, we have reached the end of week 6 for the massive open online course for the University of Nicosia's master's degree in digital currencies. I'm your teacher, Andreas Antonopouloss. I will be happy to answer more of your questions next week, week 7, same time, same place, although we might change the time by 1 hour. Stand by on that. We will find out and send out a notice soon. And I look forward to the great questions you'll be asking. Remember to ask your questions in the forum to give us time to prepare, but also to have great conversations with your fellow students, and have a wonderful weekend. See you next week, everyone. Bye-bye.